Hello, my name is Mitchell Schoenbrunn, and I'll be your instructor this year for Pre-Calculus 108 at University of San Francisco. As you probably know, I will not be here on Wednesday, your first day of class. That's because I will be up in Oregon seeing the solar eclipse of the sun. Sorry I won't be here to meet you all on the first day, but we will make up for it on Friday, the second day. I prepared a short lecture on sets, which is section 1.1 of your book. You should probably also take a look at that section. Sets are a fundamental part of mathematics, a very important part, but fairly straightforward and simple. So let's get started. A set is just a collection of objects. The objects, each individual object, is called an element of the set. Sets are very general and very abstract. Here I have an example of a simple set, orange, banana, apple. Now, even this is open to interpretation. Do I mean an orange, a banana, and apple? Or do I mean the words orange and apple and banana? And usually what I'm indicating is clear from the context. If not, it should be explained. These elements all have something in common, but that's not necessary for a set. Okay, here we have another set which consists of San Francisco, umbrella, and decimal point. Now, if I meant the words San Francisco, umbrella, and decimal point, they would have that in common, that they were words. But if what I really mean is San Francisco, the city, an umbrella that you use in San Francisco, or a decimal point, they're very different types of objects. And as I said, sets are very general. This is a perfectly valid set. In mathematics, we're generally interested in sets of mathematical objects. You already know many of these sets. Let me give you a few examples. Okay, we're going to look at a number of different types of sets, mathematical sets. The most common one we will deal with is a set of numbers. We could also talk about a set of geometric objects, a set of all squares or triangles or line segments. Polynomial expressions, you could have a set of polynomial expressions. This is an example of a polynomial expression, x squared plus 5. We'll talk about this later. This is a second degree. We could talk about a set of all second degree polynomial expressions. Finally, I want to point out that a set's elements can also be other sets. You can have a set of sets and therefore a set of sets. There's no restriction, there's very little restriction on that. I want to talk now about set notation, meaning how do we describe a set? There are a number of ways we can do this. We can simply use words, written or verbal. For example, I could say the set of all numbers between 1 and 10. Or I could be more specific, I could say the set of all integers between 1 and 10. Or the set of all fractions between 1 and 10. We can use bracket notation, meaning these curly brackets, and just write a list of objects, a list of elements that we want in the set. In this case, the set has 3 elements, the number 1, 2, and 3. We can also use bracket notation to describe the set using an expression. Here's an example. Inside of the brackets I have x, vertical bar, x greater than 5. We read this as x such that, that's how you convert the vertical bar, x such that x is greater than 5. this means is numbers that are greater than 5. Sometimes you'll see me use, instead of the vertical bar, a colon. It's just an alternate way of saying such that. Here's another use of the curly brackets with an expression that I'm going to translate for you. This means x squared such that, I'm using the colon here, such that x, and now here's a new symbol you may not be familiar with. It looks a little bit like an E, but it means member of. Okay? So x squared such that x is a member of, and now I'm using a new symbol here. I'm using a very stylized n. That n is the symbol in mathematics we use for the natural numbers. The natural numbers are the whole numbers starting at 1. 1, 2, 3, 4, and odd into infinity. So again, this expression is x squared such that x member of n. Now you might say, well, what is that? Well, if we start with 1, we can see that we want to write this as a list. 1 becomes 1, 2 becomes 4, 3 becomes 9. And then sometimes I'll use 3 dots here as an ellipsis, meaning going on, typically on to infinity. Here are 3 sets I want you to look at. This set we've seen earlier. This is just the list, the numbers 1, 2, and 3. This is what we call a finite set. The number of elements is some finite number. This set, however, written 1, 2, 3, ellipsis, means all the natural numbers, 1, 2, 3 on to infinity. This is an infinite set. That is, the number of elements is infinite. It grows without bound. Finally, take a look at this. X such that x is greater than or equal to 0 and less than or equal to 1. And I haven't stated it, but I mean for all real numbers, x. This also is an infinite set. So sets can be both finite and infinite. Interestingly enough, maybe we'll show this in class someday, there are actually more elements in this set than this set. That sounds contradictory. How can 2 infinite sets not have the same number? They're both infinite, right? Well, in fact, we can show mathematically that if we match up every element of this set with an element of this set, there are always elements left over. Finally, a set can have no elements. There's always a set that has no elements. We call this set either the null set or the empty set. Both of these symbols are ways we describe the null set. Here we have just the not symbol you're familiar with, and here we have the bracket notation with nothing inside of it, and that's also the null or empty set. If you ever see this symbol on a quiz or an exam, and you're asked, is this the empty set? You might be tempted to say, well, of course it is. In fact, this is not the empty set. This is a set which contains one element. That element is the empty set. So this is a set with one element. It just happens to be a set which is empty. Now we're going to look at some operations you can do on sets. First operation is called the union of 2 sets. By the union of 2 sets, we mean a set which has all the elements of either set. So, for example, in the case here, we have a set 1, 2, and 3. And this is the union symbol. It looks kind of like a big U. It's not actually a U. But it's easy to remember. Look at, you see U and you think union, right? We're going to find the union of the set 1, 2, 3 and the set 3, 4, 5. That is, sets with those numbers. Here's the union of these two sets. Notice it has the elements 1, 2, 3, 4, and 5. Also notice that while both sets have the element 3, 3 is only represented once. Each element of a set is unique, and there's only one 3. It can be in both these sets, and it just appears once in the union. The second operation on sets we're going to look at is the intersection of two sets. The intersection of two sets itself is also a set. It's just a set whose members are represented in each of the other two sets. Okay, here I have an expression for the intersection of two sets. The first set has the numbers 1, 2, and 3. The second set has the numbers 3, 4, and 5. This is the intersection symbol. Unlike the union symbol, it doesn't mean anything, but you can remember it's the upside down union symbol. It's the other symbol we often use with sets. Now, the intersection of these sets is just a set with the number 3. I think that should be clear. Okay, I've changed the expression just a little bit. I eliminated 3 from this set. Now what's the intersection of these sets? Well, it doesn't have any members, so it's the null set. Just as a reminder to some of you, often when dealing with sets, it's easier to look at them using a Venn diagram. Venn diagram. The Venn diagram, you just put circles or other kinds of borders around your sets, and you can indicate things like unions or, in this case, intersection here. We've got the intersection in the area that's inside of both sets. Often when we're talking about sets, just like with algebra, we'll use a variable to describe the set. So in particular here I'm representing this set 1, 2, 3 by the letter A, and I'm representing the set B by 3, 4, and 5. I can write expressions like A union A. Well, the union of any set with itself is itself. A intersection A equals A, that's always true. And for these two sets, the A intersection B, as we saw before, is just a set with the number 3 as its only element. Here are 3 sets I want to use to demonstrate. Here are Here are 3 sets I want you to look at. Okay, now I'm going to talk a little bit about, just as with numbers, where we have an algebra, we often talk about sets, the algebra of sets. Often when we're talking about sets,